Hello, everyone. Thanks for coming to this talk. I'm Javier, and I will talk today about my experience porting a couple of framebuffer device drivers to the DRM subsystem. A little bit about myself. I'm a Linux and Fedora developer for a long time. I work as a principal software engineer at Red Hat in a team that is building an in-vehicle operating system. A disclaimer here, I'm not really a graphics expert, even though this talk is about graphics. So please feel free to correct me anything that I could get wrong in this presentation. So what's the motivation here? Why did I start with this effort of porting some framebuffer device drivers to DRM? So last year I moved to a new team inside Red Hat, and one of the responsibilities of that team involved doing some graphic work. And since I'm not an expert on this, I thought that it would be good to delve more into DRM and learn its internals. So then I subscribed to the mailing list, start looking at the patches and reading the conversation that were happening there. And at the time, there was a thread about some discussions between the gaps that fbdev and DRM had. And some people were making recurring claims that fbdev was simpler than DRM and that writing drivers for fbdev was easier. And another one was that even though DRM make a good job scaling up to support very complex graphical devices, it didn't really do a good job scaling down to support very simple devices. Since I wasn't familiar with neither fbdev nor DRM, I didn't really have an opinion, but I wonder if those claims were true or not. And in one of the threads, it was mentioned that there were a family of very simple display controllers that were supported by fbdev, but that weren't supported by DRM. So then I thought that maybe if I could get one of those and try to port the fbdev drivers to DRM, that would be a good learning experience for me to get more familiar with DRM. So I noticed that I could buy those easily, and they were fairly cheap, so I did that. So these chips, the Solomon SSD 130X, are a family of very simple monochrome OLED graphic display controllers. They support different transport buses like parallel, I2C, and SPI. And as was mentioned, there was existing support in fbdev. It was split in two drivers actually. There was one driver in drivers video, that is the SSD 1307FP, that only support I2C, and there is another driver in staging that also support SPI. So what I did was to take these two drivers to port into a single SSD 130X core driver, plus some driver for I2C and SPI. So this is an image of two displays that are running some tests. The one in the left is using SPI as a transport, and the one in the right is using I2C. As you can see, even though the display controller is for monochrome displays, some displays comes with different pixel colors. Instead of white, the one in the left is using a blue pixel. So the question was it easy to port this or not? Because that was the goal of the experiment, to figure out how hard it would be for someone like myself that didn't have previous experience writing DRM drivers to port an fbdev driver. And as a matter of fact, it was very easy to do the porting. I was actually surprised how easy it was. Just to give an idea, this is the timeline of the events as it happened. I read in the mailing list that there weren't support in DRM, so I noticed that I could buy online. I only found the I2C one to buy, so I bought that one. 2 days after that, the displays arrived at home. That was on a Friday, so then I thought that maybe I could use the weekend to like get familiar with DRM, with fbdev, and start with this porting effort. And it turns out that by Monday, I actually had a working driver, and I could share it in the mailing list. Of course, I needed a few iterations for this to land, but that's like the normal Linux kernel development process and nothing particular for DRM. So another question is, why was that easy to port? And I enumerate the reasons, in my opinion, that explain why it's easy to work and to write DRM drivers. And the first one is that for very simple display devices, there are a lot of existing drivers in the tiny directory that one can use as an example and as a reference when are writing like drivers for these kind of devices. The other one is that DRM has a lot of helpers that driver authors can use. So you don't really have to write a lot of boilerplate code when you are writing a driver, and only need to focus like in the actual logic of the device. And these helpers are like very well documented. I would say that DRM is probably one of the subsystems that has the best documentation, in my opinion. Another thing that is unique, I would say, about DRM is that it's the community, and I found that it is like just super helpful. It was very welcoming from the beginning. So this is the process I followed to port the driver. Even though this the process I follow, I think that it's DRM enough that it could be used for someone else that is doing something like this. So the first step for me was to use existing fbdev driver to have like a baseline to do testing and to run some fbdev programs to make sure that you have a proper setup to work on the DRM driver. For that, I use the SSD 1307 FB driver because that's the one that supports X.Org, and I only had an X.Org display at the time. The next then is to find a set of fbdev user space program that you can use to test. For that, I found that Gert has this fbdev repo that has a lot of programs, so it's a good has good test coverage if you want to test. Then the second step was to find a DRM driver that was for a device that was similar to the one I was using. And I found that in the tiny directory there was a repaper driver that was for an e-ink display. So that was similar to the one I was working on because that display was also monochrome. And I actually took some good ideas from that driver. For example, the fact that the primary plane is exposing an XRGB format, even though that's not supported by the hardware, but that's allowed to use like any user space program, and then the driver internally converts to monochrome. So I actually did the same. The next step was then to figure out if there was any common code between the DRM driver I was using as a reference, I was repaper, and the one I was working on. And I found that this format conversion helper that the driver was using would be a good candidate to propose as a DRM like format helper. So that could be shared between the two drivers. And once I had the driver working, then the next step would be to use the DRM fbdev emulation layer to make sure that the fbdev test programs that I was using to test the old fbdev driver were also working using the new DRM driver. But it's important also to test using proper like KMS programs. And also FBCon. This was a mistake I did because I wasn't testing FBCon because the display is so small that I wasn't thinking about like having a VT there. But then Gert test, and he sent me some fixes after the drive land. So I have different attempts on how to structure the driver. The first one was to implement as a tiny driver, because I was using the drivers in the tiny directory as a reference. And this is for drivers that are for very simple devices. But it's expected that the drivers there are implemented as a single source file. So that would be suitable for an I2C driver that I was working, but then I thought that once I add like SPI support, because I was able to get an SPI device later, then it wouldn't be like a good fit, because I would need like more than one source file to implement the SPI. If I want to have like a well structured, because having like both I2C and SPI in the same file would be like not well organized. So the second attempt then was to have like a Solomon directory, and I put there like the core driver and also a driver for I2C and SPI. Those transport drivers only set up like a register map so that the core driver is independent of the transport that you are using. So before going into the details of what I have to take into account in the drivers to the porting, I will talk a little bit about the KMS display pipeline. This is only enough information to get the context that we need, so it's not an in-detail explanation. So the KMS display pipeline looks like this. This actually comes from the official DRM documentation. So you have the DRM frame buffers that are abstract memory objects that provide a source of pixels. This is created by user space. Then you have the planes that are the actual image source that are blend or overlaid by a CRTC. And then the CRTC pushes that to one or more encoders that are the ones that take that pixel data, transform in a format that can be displayed in a display sync, and then the connectors are the actual physical connectors to the screen. The way that this is implemented in DRM is you have a data structure like DRM plane and a set of operations to operate on that object. In the case of of very simple drivers, like the one I was working on, most of these operations can be actually handled by the DRM helpers. So as a driver author, you only need to define a few of these. Like for example, in the DRM plane, you need to implement an update plane. That is when there is an atomic update for a plane, because that's specific of your device. And also a disable plane if you want to disable that plane so that it's not scanned out. For the CRTC, it's similar. You need to define, like for example, a mode valid to check that the mode is valid, or an atomic check to check that like the atomic mode setting is correct. For the encoder, you also define like an atomic enable disable to enable disable an encoder. And for the connector, you need at get modes that list the resolutions that are supported by the screen. In the case of the Solomon chips, that's you only support like a single resolution. That's hard code. But for example, if you had like a HDMI monitor, then you will get that using EDID, for example. On top of that, DRM also support like a mid layer that is called simple-KMS, or the simple display pipeline, that basically is a layer on top of the KMS pipeline that abstract drivers away of all this complexity and components, and also provide a set of helpers to operate in that simple display device instead of operating on the specific components. And this can be used when you have a device that only support like a full screen scan-out buffer that is feeding on a single output, like in the case of the Solomon chips. And as mentioned, these operate into this simple display pipeline entity instead of like different objects like CRTC, plane, and so on. And in fact, when you are writing a driver that is using this simple display pipeline infrastructure, you basically ignore the other components like encoders, connector, plane types. So you only have like a primary plane, and that's all. And using this makes like writing drivers easier. In fact, most of the tiny drivers are using this mid-layer. So when using the simple-KMS, then a DRM plane, a CRTC, an encoder and connector, all those are taken as a single entity, and you have a single set of operations to operate in that simple display pipeline instead of like the operations for each component as we saw before. So you have like a mode valid to check the mode, an enable and disable that allows to enable, disable the pipeline, and an update when you have like a atomic mode set update. Now, the first iteration of the driver, the one that landed, was using simple-KMS. But then talking with Thomas Zimmerman, he mentioned some of the downsides that he saw with simple-KMS, and I actually agree with him. So I port the driver out from simple-KMS to use like the full atomic mode helpers. The reason why I did that is that simple-KMS may not be like the correct layer of abstraction for simple drivers. Like, it's true that it makes writing drivers easier, but at the expense of conflating the concept of CRTC and plane. Because the problem is that all that, as I mentioned, like the plane, CRTC, encoder, connector, are treated as a single display entity, but the helpers don't operate into this simple entity. But instead, the helpers need to access like the individual components in the pipeline. So you need to punch holes in the abstraction, and it's a leaky abstraction after all. So it makes the simple-KMS drivers less flexible because it's harder to reuse the helpers. Because, for example, if you have like I don't know, a device that enable and disable the CRTC is similar, but updating like for example the display frame buffer for scan out is different, then you cannot reuse that helper. So instead, if you use like the normal atomic helpers, that's much more flexible because it allows the helpers to be shared between drivers. And also after porting the driver from simple-KMS to use like the atomic helpers, I noticed that I didn't have to add much more code. So simple-KMS isn't really that simple after all. It's my opinion even. So I think that it's better if we just focus on improving like the atomic helpers instead of having this mid layer that doesn't really add that much value, in my opinion at least. So yes, for this reason, some drivers were changed to use atomic helpers. For example, fbDRM, UDL, others, and I did the same for SSD 1300X now. Okay, so writing a DRM driver is similar to other subsystems, like you define like a structure, you register, and so on. But I think that the important bit that I had to focus on this was in the frame buffer management. So the first step was for me to understand how the frame buffer memory was handled by fbdev drivers. So basically, the drivers store the frame buffer memory into a field of the fbinfo data structure. This is a union. You use screen base if this is I/O memory, or screen buffer if it's stored in system memory. For example, in the case of the SSD 1307 FB driver that I was using, FB info is allocated, and then a set of pages for the frame buffer, and that's stored in this screen buffer field. Then the driver also has a set of operations to operate on that frame buffer, like write, blank, fill rectangle, copy area, do an image split, and so on. All these operations at the end call to this helper that is update updates the rectangle. And what that function does is basically take from the frame buffer the monochrome pixels and fill into a data array using a format that is specified by the display RAM, and then write that information using I2C or SPI or whatever transport. In the case of the SSD 1307 driver, it only supports I2C, so it uses the I2C helpers to write to the device. Now, once I understood how that worked, then I had to also manage the frame buffer for the DRM driver. In the case of the DRM driver, is different because you use gem buffers. I use shmem as a backend for that, like most of the simple drivers do. So you have some helpers for that to fill all the helpers that you need. And also I use shadow buffers for the primary plane. That is also something that other drivers do, and that allows you to have frame buffers that is bigger than the display area. For example, for FBCon scrolling and things like that, is very helpful. And again, you have some macros that sets the correct helpers for you, and you only need to define an atomic update handler that copies the data from the shadow buffer to the hardware frame buffer. So in the case of the driver, what the atomic update handler does is to get the new plain state, get the old one, also get the shadow plane state, and then iterate over the damage areas to determine if that damage area is intersects with the area that is displayed, and if that's the case, then it does a blip on the rectangle. The blip, what it does is basically calls to the helper that converts, because as I mentioned, we are exposing XRGB as the format for the primary plane, so it has to convert to mono first, and then once it's converted to monochrome, it calls to update rectangle, that update the rectangle, and that's similar to the function we saw that the fbdev driver also had. So that's basically goes again through the monochrome frame buffer, takes the data, converts in the format that is expected by the device, and then write to the device using recmap, and that could be I2C or SPI depending on the transport library you're using to set the recmap. So yeah, at this point I had the driver, and I thought, okay, what I'm going to run now, because I can run like FP tests and things like that. So then I decide to run Doom. What else, right? So yeah, I did a retro console with my kids that I actually have here if someone wants to play during the break. Yeah, I wish, but since the display is too small, I will show also a video. But first, I want to acknowledge some people, Thomas, that helped me a lot reviewing the driver, but also explaining to me DRM and KMS concept that I could understand from the docs. Maxime that wrote the original fbdev driver for I2C, Noral for the one that supports SPI, and then Sam, Andy, and Gert that also reviewed the driver when I was working on. So I have here a video. So yeah, this is the console playing Doom. This is an unmodified user program because since it's exposing RGB and the driver doing the conversion to mono. But this is something that I could also run with the fbdev driver. So then I thought I should show something else. So I have here GL Mark II that is running. I don't know if you see the horse there. There is the bill benchmark. And there is also the jellyfish benchmark there. So yeah, that's all I have. I don't know if you have any questions. Yeah, it's using software rendering because it doesn't. Yes. Oh, sorry. The question is, since it doesn't have a GPU, it's only a display. What's using for rendering, and it's using Lava pipe for software rendering. Mm-hmm.
Is there other like frameworks, or other helpers such as dithering and other techniques?
So the question is if I'm using this XRGB to mono helper, and if there are other helpers like for tethering, you said. No. Actually, tethering is something that I want to explore because I think that it should be supported by the device. But there are other format conversion helpers in the DRM format helpers. But for this particular device, for tethering, there isn't any helper yet. Okay, thanks a lot then.